Hello everyone. This is week 4 of our Intelligent Agents in Learning Environments course. Last week, we had a very brief introduction to the transformer architecture that is used in large language models, and this week we are going to go more in depth about how they work. We're going to be covering what transformers are, the attention block, and the softmax function that is used within the architecture. First, we're going to be talking about transformers and how they work. We had a very brief introduction to them last week, and as we know, transformers are a specific type of neural network and machine learning model and are the core component of the current boom in artificial intelligence today. They are used in models that can take in audio to create a transcript and vice versa, creating generated speech from a given text. To start off, they break down the text input into smaller pieces called tokens, which can consist of words, parts of words, or a sequence of characters. If the input is an image or audio, the tokens can be different parts of the image or smaller parts of the sound. Each token is then given a vector to be associated with, which is a list of numbers that encode the meaning of that token. Each vector passes through the attention block, which allows the vectors to interact with one another and pass information back and forth to each other, like the context in which the word is used. For example, the word right could have different meanings depending on the context it is used in. You could be talking about the direction between left and right, or you could be talking about an answer being wrong or right. The attention block looks at the surrounding context and updates the meaning of the words if necessary. Next, each vector goes in parallel through the multi-layer perceptron layer, also known as the feed-forward layer, where it asks the vector questions and updates information about the word based on the answers. It can ask questions such as, is this a noun? Is it part of a quote? And then uses those answers to update the meaning of the current word. The vectors repeatedly go back and forth between the attention and multi-layer perceptron blocks until they reach the last word in the passage. A certain operation is used to produce a probability distribution over all possible tokens to predict what comes next. Since computers cannot understand words, we have to represent words and their meanings with vectors of numbers, and this is called word embedding. The computer asks a set of questions to determine the meaning of the word and assigns a value depending on the answer. We can use the vectors of these words and perform mathematical operations for analogies. In the example images on the right, we can see that a group of words is defined in the table at the top, along with their vector values. We can use those values to take an equation, such as king minus man plus woman, and we can see that the resulting values of that equation will be similar or equal to the vector values that represent the word queen. The model has a predefined vocabulary called the embedding matrix, which is a list of all possible words. It has one column per word, and each column determines what vector turns each word into. It can be visualized by plotting each word onto a three-dimensional space to see how words get embedded into vectors. Words that have similar meanings will tend to be plotted on the same area of that graph. Next, we're going to further explain the attention block. As we already know, the main purpose of the attention block is to allow vectors of words to communicate with each other to determine the meaning of the current word based on the context in which it is used. The main components of the attention block are the query, key, and value. The query is the general topic that you are looking for. It can also be seen as a request for information to further understand the context of the word. The key is a piece of information that is compared with the query to see if it is what you are looking for. It measures a value of how relevant it is, and it can also be a description of the query. The value is the actual information itself that is taken based on how relevant it is to your query. Multi-head attention uses multiple attention heads to allow the model to focus on multiple relationships between words at once. Each attention head produces its own context embedding, which is then added up to have a final contextual sum of the current word. Lastly, we're going to go more in depth for the softmax function. The softmax function is an operation used to turn a sequence of numbers into a probability distribution, where each value is between 0 to 1, and the total sum adds up to 1. When looking at an untrained network, all the values will be random. They will either be negative, or the sum will not add up to 1. It is the standard way to turn an arbitrary list of numbers into a valid distribution, where the largest values are closest to 1, and the smallest values are closest to 0. First, it takes e to the power of each number, which turns each value into a positive number. Then, you take the sum of all those values and divide each number by that sum, which will result in a list of numbers that add up to 1. Sometimes, there is another variable t that is included in the denominator of the exponents, called the temperature. It resembles the role of temperature in thermodynamics equations. When t is larger, it gives more weight to the lower values, and when t is smaller, the bigger values will dominate more. And when t equals 0, all of the weight goes to the maximum value, making the model go with the most predictable word. The image on the right is the softmax function implemented in Python. It takes an arbitrary list of numbers, in this case, declared as z, and applies the softmax function to each number in the list. It takes the resulting values and calculates the sum, then divides each number in the list by that sum and is rounded by 2 decimal places. The softmax function retains a relative order, but still emphasizes the larger values by applying different given functions to each value in the list. It then normalizes each value by performing the division equation to each value, which ensures that the sum of all output values will equal to 1. This will show that the larger values will become closer to 1 and the smaller values will become closer to 0, essentially stretching out the differences. If we were to replace the exp function with the id function, the values will not change. The output value will be the same as the input values because it applies no transformation to the original values. If we were to replace it with a function that takes each value and multiplies it to an exponential function with a base of 9, it would replace the standard softmax function, where the exponential function is originally with base e. The values will grow slower than the standard softmax function because base 9 is smaller than base e, which results in the larger values being less dominant. Thank you for watching.